Professor Dr. S. Gauri is the Director of EMRC of UGC and also Professor in the Department of Manufacturing Engineering, Anna University. He is the recipient of the National Award for Outstanding Academic 2011, honored by the Indian Society of Technical Education, New Delhi in 2012. He has previously been the Registrar of Anna University of Technology, Chennai. He received BE in Mechanical Engineering from Tyagarajar College of Engineering, Madurai, MTech in Production Engineering and PhD in Precision Machining in IIT Madras. He was awarded for his PG project work in IIT Madras. His main areas of interest are technical education system development, precision machining, rapid prototyping, FEA, biomedical engineering, medical image analysis, and shape memory alloys. He is a life member of ISTE, AMM, and SME of USA. He has been awarded with fellowships of research work done in surface engineering by NSF, USA in 1992 and by NSTB Singapore in 1997 to 1999. He is a visiting faculty in India and abroad in many colleges and universities, including Nanyang Technological University, Singapore, Technical University, Weingarten, Stuttgart, Germany, and taught nanotechnology. He has traveled many countries, including Germany, UK, USA, Netherlands, Singapore, Spain, Switzerland, Malaysia, Brunei, and Australia for his academic works. In addition, he got international travel fellowships from UGC, AICTE, CSIR, and DST. He has successfully completed several projects in India and abroad. He has offered technical consultations in India and abroad to MNCs such as Sony of Japan, Pratt & Whitney of USA, GE of Singapore, iGel of Australia, and also to Railways Coach Factory, Chennai. He was a member of the Technical Expert Committee selected by DST to participate in the Indo-UK Manufacturing Engineering Colloquium held in January 2012. He headed the International Joint Project on Virtual Laboratories on Mechatronics, a real-time web-based project with partners from Julius Maximilian University, Würzburg, Germany, and the University of Madrid, Spain in 2005. He is holding an international patent for the work done in micromachining during his tenure in Singapore. He is a member and director of several Tamil Nadu government advisory boards.
In this lecture, we will discuss on the extension of linear programming problem and how it is used to minimize the transportation costs, and in order to obtain feasibility, what are the methods to be used from the three methods, and how will you get a feasible solution, then how will you move towards optimality.
Transportation problem. Here, the main objective of the problem is to minimize the total transportation cost. We are not bothered about what is the mode of transportation, it is total transportation cost, and we know that without a transportation cost we cannot transport anything. It involves at least some minimum quantity. The cost cannot be 0. If the transportation cost is 0, one thing, it is a very fictitious transportation which is not existing. Otherwise, the cost involved may be 1 rupee or 100 rupees or maybe still higher per unit, and that should be minimized. And in this particular case of transportation problem, some assumptions have been made. The assumptions are just like the one what we have discussed in the earlier classes. Say this is a large industry like our country, and some factories here. So, these are the factories, and they produce certain quantity of items of the units according to its capacity. The capacity may vary or may be same, but the type of the products remains same. Can you give an example of such a product which is produced at different locations in a large industry like India, and it is distributed everywhere in the country according to the demand exists? Yes, biscuits, very good, biscuits, soft beverages, then other type of any other type of consumer items, yeah, pencils, yeah, any consumer items which has the unit value or unit cost is less, but they are required in large quantity. Almost every citizen makes use of it or need of it. And such items are produced bulk in different factories like this, and they are distributed to different warehouses here, something like that. So, the black spot is the warehouse. Now, we know the distance between each factory to each warehouse. Just like the airline network, this is the one. Similarly, for other factory, this may be for one set and that may be for something like that. You can find. That means, from each factory there are routes exist between each factory to each warehouse like this, and this blue line or the red line is nothing but the distance. This is also distance, the distance, and the transportation cost is proportional to the distance. That means, when the distance is larger, a longer distance, the cost involved is also larger. The distance is smaller or shorter, and the cost involved is also short. And each factory can produce according to its capacity the items called supply, and that can be put as Sij, S subscript j, Ij, and warehouse there is a demand exists, and that is called Dij, demand. And the cost involved is given as Cij, that is unit transportation cost. Unit transportation cost. Now, we know the supply of each factory, we know the warehouse demand of each warehouse, and we know the distance and hence the cost of transportation from ith factory to the jth warehouse. That is ith factory to the jth warehouse, something like that. Si 1, 2, 3, 4, Dj, the warehouse is also 1, 2, 3. From ith factory to the jth warehouse, the cost involved is Cij to transport 1 unit. This 1 unit can be either a single, or it may be a box of items, or it may be a cartridge of some items like that. Maybe 1 unit, it is a large one, just like a printer, if we take a one, or it is like a biscuit. In a box of biscuit, there may be 36 biscuits, or in a tin there may be 144, something like that. Still, that is called 1 unit. So, that is called unit transportation cost. Now, the question is, how many units can go from each factory to the each warehouse according to the supply or the capacity and according to the demand existing, so that the total transportation cost of all the items transported will be the most minimum, that is IA. It is just like the assignment technique, but in the assignment technique the number of employees of each category is only 1, and the number of machines available are 1, just like there are employees like John, David, or Murugan or Balu. There is only 1 John, 1 David, 1 Murugan, 1 Balu. Like that, if there are machines, a lathe, a grinding machine, a milling machine, a drilling machine, means there is only 1 in each category. So, the method adopted is somewhat different than the method what you are going to use it. Here, the number of items available from each factory is not 1, it may be 10, it may be 100, it may be 50, 75. Similarly, the compare with the number of machines, here the demand, that the demand existing also is not always 1, it may be 10, 20, something like that. You remember, one employee or one machinist is assigned to one machine, finished. That machine will not acquire any more operator, that operator cannot do any more operation any more machines. One is just like a monogamy, but here if the supply is from the factory is 50, there is no condition that the whole 50 items should be given or distributed to one particular warehouse. Out of 50, one may be receiving 10 units, other may be receiving 20 units, other may be receiving the balance according to the distance and the demand what exists. So, we are going to distribute them, we are going to divide and distribute them. So, that is called the modified distribution technique. This is the technique adopted is modified distribution technique. And finally, the total transportation cost will be minimum. The factories, the total demand will be distributed, and that means the total supply will be distributed, that total demand will be satisfied. That means, each factory will distribute all the produced items and each warehouse will receive the items according to the demand is satisfied, completed. Without that, we cannot say the problem is complete. So, okay. This is a some sort of a prelims or introduction about the transportation problem. Now, let me go to the problem. Please note, the warehouses are represented in the column wise where there is a demand. The factories are known as a source or supply, they are represented in the rows. So, this is supply, this is demand. Now, each warehouse requires some items, maybe 50, 75, 100, 125, 60 and 40. Similarly, each factory can supply certain items, maybe like 40, 40, 160, and the transportation cost from factory 1 to warehouse 1 may be 5. Seventeen, 11 and 19, and here 15, 21, please note the black one cell entries are the Cij, that means we take this C11 is 10, C12 is 15, C21 is 19, C44, what is C44? C44, 19, very good. Like that the cell entry is given. So, this is the data given in the problem. All of you understand? Factory, warehouse, demand, supply. Now, the question is how many items the factory can supply to each warehouses or set of warehouses, and the warehouses will receive according to the demand, according to the distance. So, the total transportation cost is minimum. To transport one unit from factory 1 to warehouse 1 is 10. To transport one unit from the same factory to the warehouse 2 is 15. Unit cost is 20, 17, 14, 12 like that. Now, if this is only one set is given, you can say which is the smallest transportation cost, 12 or 10, yeah 10. That means, this factory is closer to that warehouse. That is a, so you will allocate only 10 here. How many units you can allocate here? How much you can supply? 40. How much? There is a demand here? 50. So, how much you can allocate here? Can you allocate all the 50 here? No, that fellow cannot eat. For example, if you take this case alone, this is the supply is 160, the demand is 75. So, how much you can give? 75. Over stuff is not possible. And this is a case where the supply is 40, but the demand is 50. Again, the requirement is more. The fellow says, just like you ask pocket money from your father, I want every day 100 rupees. The father says, my monthly salary is less than your pocket money. How can I give? No, the father cannot give. So, whatever the father can give, you have to accept it, even though your demand is more. So, like that, even though the demand is more, it can supply only 40. So, you can put 40. So, simple logic, compare this to whichever is a minimum, put that allocation. Clear? It's okay. So, but there is only only one factory, one warehouse, or one factory set of warehouses. There are 5 factories and 6 warehouses. Now, we have to distribute them here, here, here like that. So, that we will find whether the cost is minimum. So, that is a question. Now, you may ask, sir, how this is LPP model? They have told you the Cij is constant, the supply and the demand are constant. Only thing, how many items we are going to allocate here, here, here is a variable, and that value you are able to find out. We are going to find out, and initially we do not know. So, some may be allocated here, some may be allocated here, some may be allocated here, may not be. X11, X12, X13, X14, X15, X16 like that. Here X21, X22, X23 like that. Initially we do not know, just like you remember your simplex problem what you have done, X1, X2, X3, finally X2 was 2, z equal to 4, remaining X1 and X3 becomes 0 like that. Here you write down all the possible variables. How many variables will be here? 5 into 6, 30 variables. X 5, 6 is the last variable. There are 30 variables. Out of 30 variables, we do not know how many of them 0. And again you can make them X11, if you allocate something here, allocate something, the sum, if you sum up all the X1, X12, X13, X14, X15, X1, that will be equal to 40. Similarly, X21, X22, X23, X24 like that equal to 40 like that. Similarly, here X21, X11, X21, X31, X14, X41, X51 you sum up, that is equal to 50 like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 equations, constraints can be made. And how many variables? 30 variables, 11 inequalities, 11 constraints. Solve it by simplex, even by take simplex technique, it is difficult. You cannot, maybe 3 hours or 4 hours may not be sufficient sometimes. So, even though this has a LPP principle behind it, a different technique has been proposed, so that the problem can be solved fast and easier. In those days there was no computer, but still with the computer the same technique can be adopted, so that the problem can be solved so fast. Clear? The major assumptions here are, whatever the supply, whatever be the demand, whatever be the transportation costs, they are fixed. They are not changing, fixed. The data given is fixed, dynamic. It is not dynamic, it is static. Subjected to, there is no natural calamity or other things, nothing. The things will not vary. The cost, the supply, the factory, if it says I can supply 40 units, it will supply always 40 units. No machine breakdown, no labor unrest, no strike, nothing, no, it will supply. Similarly, the warehouse 50, 75, the demand is there, always there is a demand. The warehouse will not say, no, the customer is not there, I am unable to sell, no. Similarly, the transport cost, whatever 10, 15, that remains same. The bus goes in time, the lorry goes in time, there is no maintenance problem, no theft, no accident, nothing like that, the transportation cost remains same. These are some assumptions what we make. Okay, now, we have to allocate some of the units, so that the total supply and the total demand can be satisfied. Before you go to the problem to solve, check whether the total demand is equal to total supply. That one thing you should make. What is the total supply? 40 plus 40 plus 160 plus 60 plus 150? 450. What is the total demand? 450. So, we can proceed. If the total demand is not equal to total supply, what should we do? Go to the next question. You should add, for example, this is not there. If this warehouse is not there, what will be the total demand? 410. Still the total supply is 450. So, for the 40 you have to put the 40 here, but the cost is not known, because you are producing, you are making a fictitious warehouse in order to make the condition satisfied for the purpose of calculation. So, you are creating a warehouse which is not existing. So, put that warehouse 6 which is not existing, put 40 here, instead of the 12, 18, 19, 20, 29 you put 0, 0, 0, 0, because it is an ideal fictitious, nobody exists like that, clear. So, at that time put 0, 0, 0, proceed. If one warehouse, one factory is not there, if the 150 is not there, what will be the total supply? 300, but still the demand is 450. So, for the 150 you put another fictitious factory, put 150 here, instead of all the Cij put 0, 0, 0, that is all. So, some allocation will be made there. The smallest, for the first allocation will be going there only, because that is the smallest cost. By putting that, we are optimally distributing the remaining distribution. That is why we have to do that. Okay. So, first we check whether the total supply equal to total demand, then go for solving the problem. And this problem is solved in 2 stages. Transportation problems, it is done in 2 stages. The first stage, to find out a basic feasible solution. The second stage, find out the optimal solution. Find out the basic feasible solution, and afterwards go to the next one to find out the optimal solution, OS. Do not say operating system, it is optimal solution, because this problem has some weakness, because it has to be distributed according to the supply and the demand. So, that cannot be directly solved just like the assignment problem what you have done by Hungarian technique. You are splitting, now it will know the 40 can go anywhere here, from 50 the 40 has been given here, the balance 10 may go either here or here or here, like that. So, I am splitting the items, that is why the Hungarian technique cannot be effectively used here, we have to go for the other technique. First stage, find out the basic feasible solution. Basic feasible solution means a sort of rough allocation. In simplex technique or anything, or if you remember your graphical technique, the corner points of the convex polygon are the feasible solutions, basic feasible solutions. That means, basic feasible solution means they satisfy all the constraints, at the same time non-equality constraint also 0, non-equality, no, 0, sorry, non-negative constraints. It satisfies the non-negativity constraint also, basic feasible solution. So, all the corner points in the convex polygon will satisfy all the constraints including the non-negativity constraint, but any one of them, at least any one of them will give the optimal solution, at least any one of them. So, we are going to find out what are the feasible solution, what are the corner points, something like that by this technique. Then we check whether that solution is optimal or not. If it is optimal, well and good, stop. If it is not optimal, proceed further.
From our discussion, let me summarize that the transportation problem is an extension of LPP, that means linear programming problem, where the objective is to minimize the total transportation cost to modify the distribution of goods from factories to warehouses as per the supply and the demand which exists. This can also be used for maximization and production scheduling problem, etc. The important questions are: number 1, what are the 3 methods to estimate feasible solution which are standardized? What is called modified distribution, that is called MODI method. Third question, what are the operations to be carried out to convert a minimization problem into a maximization problem or vice versa?